Alright, now we are in part 2 of our lesson here. So you can see on the lecture sheet, on the handout, you should have printed this out, we have a bunch of these solids that we can consider these prisms here. So one of the things about solids is, just like with any other shape, just like with any other geometric entity, we can divide them into categories here. So just like how, for instance, with triangles, we can divide them into isosceles, equilateral, and so on here, we can do the same thing in this situation here. So for something like this, prisms are going to be one class of these solids here. So I'd like you to take a look at this here and pause the video and jot down what you note about these solids here. So these are considered prisms, but these are not. Using what you know here, I'd like you to jot down to the side here what you note about these prisms, and we'll talk about that when you come back. Okay, now we're back here. So the first thing to note about this is that these are all prisms here. Notice that all of them have straight sides. There's nary a curve in sight here. All of these have just very jagged, pointed, angular things here. So the first thing, we actually can create a bigger category for these solids here and refer to these as what are known as polyhedra. So you can see on our definition, we define a polyhedron as a solid that's bounded by flat polygonal surfaces. Every single one of these surfaces here is a polygon. We have some rectangles here. We have some parallelograms and all this other stuff here. We have the solid that's bounded by flat polygonal surfaces. Now, when we talk about these solids here, so you note that for each one of these, one of the things you may have noted here is that each of these seem to have two identical faces. So for instance, in this over here, right, you can see that we seem to have a top face here like this and a bottom face here like this as well, and they seem to be identical. The same is true over here. We see here this front face here, this front trapezoid here, and this back trapezoid, and they're both identical. The same is true here with two hexagons here and two pentagons here. So we seem to have that case here. So one important thing to note is that we seem to have two congruent parallel faces here. Furthermore, you'll note that along the outside here, we seem to have a bunch of rectangles here, right? So here's rectangles here for this hexagon. These are joining the hexagons together. For this rectangular box here, we have a bunch of rectangles, i.e. squares. Over here, you can imagine this, something like this here. You have a bunch of rectangles along the side. Now here, we kind of don't have that here, but some of you might note that this prism seems to be a little tilted, right? Like, it's not standing up straight. Someone built it wrong. That's not necessarily a bad thing, mind you. It just happens to be a prism that was built, it's not straight, straight up and down here. So in this situation here, all of these are prisms here. And indeed, if you look at our definition, we can actually use that to come up with a definition. We can say that a prism is a polyhedron, so note the polyhedron definition from before, and it's composed of two congruent parallel bases here. So those flat sides we refer to as the bases here, and the parallelograms are joining them here together. So we say parallelograms here to allow for these cases here, things like this. So in this case, the congruent sides here, we refer to these as the bases here. So here's a base here, and here's a base here, even though the bases are not necessarily top and bottom here, okay? You also note that each of these things have each of these prisms here have specific properties here. So for instance, something like this, we can say this is a trapezoidal prism because there are trapezoids that are created as the bases here. Here we have hexagons and top and bottom, pentagons and so on. You also note that these look regular here, and that's going to be important later on. So we can talk about these sorts of things here. So for instance, something like this, you can see that this second one here, the most important part is it's a hexagon, and the regular hexagons, and it's straight up and down. So in this case here, this thing we refer to as what is known as a right. So right refers to the fact that it's straight up and down. And this is a regular hexagonal prism here, okay? So it's a right regular hexagonal prism, something like this here. We can consider it as such, okay? Regular hexagonal refers to the shape of the base here, so we can see that the base is important here, and prism, of course, to dot it up. So in the same way here, so this prism here, this is going to be a little bit different here. Now, it's not right anymore. This one's it's kind of slanted, so we refer to this as oblique. So we call this oblique here. So this is oblique, okay? And again, we have a regular, now in this case, the base is a regular pentagon, so it's a regular pentagonal prism here, okay? So we have that here, okay? So we can just use this nomenclature to figure out how these sorts of solids work out here, all right? And we'll see how this works here. All right. So let's move on to the second half of the lecture notes here. So in this example, as you can see, there's a right regular triangular prism here where BC is 4 and CF is 6. So we can label the pieces here. So here's 6, BC is 4, something like this here. Now, this is a right regular triangular prism, which means the bases are regular triangles, i.e. they're equilateral. So we can fill in everything here. So these are all 4s here. DE is 4, EC is 4, EF is 4, DF is 4 here. And we have these 6s here as well. So first off, we're going to calculate the sum of the areas of the lateral faces of the prism. Well, if you imagine the solid here, you can think this is just like a prism or a Toblerone here. You can kind of unwrap it here. And by unwrapping it, you see that when you do, you end up with what appears to be 3 rectangles here. So 1, 2, and 3 here, right? You can see that we can kind of unwrap this, starting, so like, for instance, this here will be A, C, F, D, and then we can continue around like so here. So now we can see FC, this bonds with BE here, BE like this, and then finally back to AD here. So we can see that basically we can kind of unwrap all this into these. So now it's just a matter of finding the 3D areas. So this is pretty straightforward. Each of these is a rectangle with side length 4 and 6. So the area in this case is going to be 4 times 6 times 3. Right? Because in this case here, we have each of the rectangles is one area, as area 4 times 6, and there are 3 of them. So this is going to be 24 times 3, which is 72. Okay? Now, in the second situation, we want to calculate the total surface area of the prism. Note that the total surface area is really just what we have already. It's this stuff here. But then we also have to add, so it's going to be this, so we're going to call this the lateral area, LA. It's going to be the lateral area plus the 2 bases here. So it's going to be 2 of these triangle thingies. Luckily, the triangles are very easy here. These are each equilateral triangles of side length 4. So you can use the formula for this here, s squared radical 3 over 4, or you can use the 1/2 base times height here. So I'm going to do this, so you have s squared radical 3 over 4 here, so that's 4 squared root 3 over 4. In this case, we're going to cancel those out, and we're left with 4 radical 3 here. But there are 2 of them, so that means the total surface area is going to be our lateral area plus 2 triangles here. So that's going to be, in this case, 72 plus 2 are triangles, so it's 2 times 4 radical 3, and that yields a 72 plus 8 radical 3 here. Okay? So that is our total surface area. Now, for the volume of the prism here, the best way to think about the volume is that you can think of this as, a lot of you may have considered this prism here as sort of a stack of these shapes moving upward here. So, or rather, in this case, moving backwards, but because we're having it on the side. But you can think of these as a bunch of these shapes stacked on one another. Now, unfortunately, I'm not going to be able to prove this here, but intuitively, it makes sense that it's just a bunch of these bases here, where B here is the area of the base. And then we also have the height. So how tall it is because it's going to go back 6. So it's going to be times the height, or the altitude here. So we can go ahead and calculate this. So this is easy because we calculate this already. This base came from before. We know the area of this is 4 radical 3. So I can write this as 4 radical 3. And the height, well, it goes 6 units back. So it's going to be 4 radical 3 times 6. So that's 24 radical 3 here for our volume. So that actually gets us a lot of good things here. So as mentioned before, we now have several formulas. Our volume here, for instance, something like this. Our volume is the area of the base times the height. Again, we have capital B to represent the area of the base here, times the height of the prism here. Now, going back to what we had before, we see that this, notice how essentially what happens here, we had a strip of rectangles here, but this strip of rectangles is essentially a big rectangle itself, right? We went from A to C to B back to A to C to B back to A. That's the perimeter of the object here. If you don't believe me, check the one in the back. We went from D to F to E and back to D. So we have again here. So we can actually simplify this and say something about the lateral area. The lateral area in this case is going to be P, and this is going to be the perimeter of the base. And again, we're going to multiply this by the height because it's a rectangle, right? The height is just basically the height of the prism here. And from what we had before, we see that we had our surface area is this, lateral area plus 2 times the triangle. So we can do the same thing here and say that our surface area in total is going to be equal to the lateral area plus double the base. Or if you want to rewrite this, you can write this as PH times, P times H plus double B here. So you have these 3 formulas here to help you with prisms.